Okay, today we derived the Bernoulli equation, and I want to just quickly go over the assumptions behind it and the structure of the equation. I'll just call it Bernoulli, and of course I mean the Bernoulli equation. The key assumptions behind the Bernoulli equation lie in the assumption of a steady flow field, so steady flow, constant density flow, and inviscid flow, so no viscous stresses. So these three are the assumptions that go into our analysis. There's one more that will emerge when I write down the equation. The approach is to integrate the Euler equation, and I'll just write Euler equation, along a streamline. And so if the streamline direction is S, then the Euler equation would be that minus d by ds of p plus gamma z is equal to rho times as. Can't tell this is an S over here. Here we go. So it's basically forcing related to acceleration. Okay. When we do that integration along a streamline, what we find is the Bernoulli equation, which tells us that p over gamma plus z plus v squared over 2g is equal to a constant along streamlines. And that's our fourth assumption that I want to emphasize is along a streamline. So steady flow, constant density, inviscid flow, along a streamline. Once those conditions are met, then we can use the fact that p over gamma plus z plus v squared on 2g is a constant, and apply it in the same way that we used p's metric head previously, going, say, from point 1 to point 2. Now we have a relationship between velocity, elevation, and pressure. And to put this into the context of energetics, we could think of this term, the v squared term, as the kinetic energy. We can think of the vertical position term as our classical potential energy. And then finally, our pressure term would be this new form of potential energy, which I'll call the pressure potential energy. And when analyzing flow in fluids, basically we can have energy moving between these three boxes, and in the case of inviscid flow and steady flow, energy is conserved. So if we have something that's, say, at a high elevation that then flows downhill, that potential energy gets converted to kinetic energy. On the other hand, if we had something that was at, say, high pressure, so P over gamma was large, and then we punctured a hole in the container, say, picture a balloon, that pressure potential is converted to kinetic energy. Of course, you could also then use that kinetic energy to raise the fluid upwards, going to higher elevation, and then that could to return to pressure or not. So you have this movement of the energy between these three components, but subject to the constraints of our assumptions, the sum of the three has to be constant, and that's the way we'll use the Bernoulli equation.